Very excited to be here at BrisTech. So this is not an effective use of your 10% time, right? This, the thing of beauty, Atari. So my hairline may say otherwise, but I was very young when Atari sort of came out and was around. I was more of a Amiga 500 man, James Pond and all of that jazz. 2D games are definitely the best, right? This extra third dimension is completely unnecessary, so much simpler to understand, but you probably shouldn't say that as a data scientist. But I want to set this in a real-world context. So I'm about to talk about Atari games, but how is this relevant to the real world? So this is how my career started out. Working on autonomous vehicle, not this one in particular. This is Stanford Stanley, which was the winning entry around about the time I was working on autonomous vehicles as a placement student of all things. And this is about 15 years ago, around about that time. Back then, they were doing autonomous vehicles in deserts and not in the sort of urban environments that the real world that you see today. But if you could train, imagine you could design a policy that basically said, if the car stays on the road, that's a good thing. If it goes off the road, that's a bad thing. And basically just reward the car every time it stays on the road and punish it when it goes off the road. Obviously, you want to do this in the real world because driving into walls and crashing, you're obviously writing off cars. You probably want a simulated environment. So I was quite surprised to find out when I've just joined a company in Bristol, Rovco, which does subsea robotics and surveying of things like offshore wind farms. And they have a little robot, it's like Johnny Five, that goes out there and captures video and can look for things like corrosion. And I was surprised to find out my own company is doing work in this field. They're looking at reinforcement learning, so the little Johnny Five robot can drive itself rather than having a human operator actually control it. I'm not done. You'll see, you heard in my intro that it had all the job titles in there, all the different fields. The marketing manager in my own company slacked me yesterday just before I came here and said, "What is your job?" Came here and said, "What is your job title exactly?" Which shouldn't be funny, right? So this is my experience. I started out with a computer science degree, and this is me becoming a software engineer. I started out in embedded C++. We all make mistakes, right? But I quickly moved into the world of big data and petabyte stores on the elephant that is Hadoop. And then I started adopting technical leadership roles as team lead, and even architects. And as soon as you start doing that, these guys don't think you can code anymore. And then I was very fortunate enough to fall into a couple of data science roles. So I was in charge of knowledge management for an organization, initially unifying all of their relational stores and microservices so they could have a single portal where you could search for a particular piece of information and get everything the organization held. But we also did a lot of work with NLP to actually look at Word documents, OneNote, and actually analyze the text in them and pick out facts from them, and then actually link those facts back to the relational stores. Think of it as a single view of a customer. And then I moved on to this blue dot thing here. So I was at a company doing indoor maps for shopping centres, airports, museums. An indoor positioning in those places is really poor. You don't have a clear line of sight to the sky, so you don't get that GPS fix. But however, you can use other things like Wi-Fi, signal scanning, accelerometer data, gyroscope, compass, and if you put all of these things together and throw them into some sort of ML model, you can predict where people are and then give them nice turn-by-turn directions, tell them they're going to miss their flight unless they get a move on. And then I thought I'd consolidate everything I'd learned and actually understand what I'd done over the past few years and did a data science degree at the University of Bath, which is where a lot of the material for this talk comes from today. They've got a very good reinforcement learning lecturer and PhD students that are very helpful. So what does this look like? So initially you want to start off comparing against some sort of baseline. So this is playing Pong randomly. So the paddle on the right here is just taking random actions. Occasionally it's going up, down, or staying still. You'll see it's not too good at playing the computer. It tends to miss the ball, right? And it carries on like this. Occasionally it manages to get one back, but it loses pretty comprehensively. And also, what does playing randomly look like in Space Invaders? So you can move left, right, fire, do nothing. For anyone that hasn't played Space Invaders, I'm sure you all have, you've got this little agent, a little player at the bottom of the screen. Hitting an alien in the bottom row here gets you 5 points, 10, 15, 20, 25, 30. And occasionally there's a mothership that flies over the top, and if you hit that, you can get a whopping score for getting it. You see the random agent it's not doing too bad, it's not doing too well, it does get hit quite often, and the mean score of playing randomly is about 200. In this particular case, it doesn't do too well. I think it gets about 90, but I won't let that play through. There we go, it's got hit again. And you'll see at Pong, we lost 20-0, or 21-0. So if you want to get started with this stuff, everything I'm about to show is an implementation of these two papers here. The second one is just an elaborate version of the first. This is the DeepMind guys, and they were the first with a breakthrough showing that you could use deep learning with reinforcement learning and actually get really good results. And they did it on Atari games. And that's what the chart here is on the left. So if you want to go away and use the code I'll show you later on, or go and implement this yourself from these papers, pick a game. You can pick an Atari game from the left, pick one above the line. That's sort of humans were measured playing these games, and the score that the mean score they typically get recorded. So if you're above this line, deep reinforcement learning that I'm going to show should do better than what a human does typically. You see up there, Pong's above the line, and Space Invaders is somewhere up there. Although I can't quite find it. Oh yeah, just there. Just next to Pong. So all the codes, all the demos I've generated and results are from this repository. This is my implementation of those. This is my implementation of those research papers. There's lots of other examples on the web. Lots of people have done this. You can find lots of tutorials. If you don't quite understand the code that I've got, you can look at how someone else has done it, or you could feel free to raise issues against my code base, and I'll respond and get back to you if you want to get going. So where do you start with this? This is one of the things I'd recommend. OpenAI Gym, it's a great tool if you want to learn to play and train a computer to play Atari games. The API is really nice. It basically gives you screen frames of what the game state looks like at any moment in time, and you can take actions. You can tell the player to go left, right, fire in Space Invaders. And it also tells you how many lives you currently have. So the typical sequence is you take an action, and then it gives you the game score back, how many lives you have, and what the current state of the screen looks like. There's not just Atari in here. There's lots of other things. There's like robotic control environments. So you can like train a pair of legs to run across the floor without falling over. So the more advanced stuff that's more relevant for the real world also exists in there. So where do we begin? There's a bit of basic terminology that you need, and I'll be mentioning throughout the talk. This is just the core reinforcement learning stuff. So the basics, really. We have an agent, so the player, it could be the Pong paddle on the right-hand side, or the player at the bottom of Space Invaders, interacting in some sort of environment. In Pong, that's everything you see on the screen. Pong and Space Invaders. Paddle, the ball, Space Invaders, the alien, the aliens, should I say, the mothership, the shields. And that agent takes actions in the environment, go left, go right, do nothing, fire. And by taking an action, you may get a reward now at some point in the future. So firing Space Invaders, you may hit an alien and get some points for that. But I've just spoken about core reinforcement learning and some terminology. What's deep learning got to do with any of this? And neural mean by deep learning, right? Because that's what we mean by deep learning, right? So this is the screen from Space Invaders. So it's grayscale rather than RGB, so it's a 2D array. But let's make it even simpler. Imagine it's not grayscale, it's just white or black, it's binary. You could design an algorithm by playing these games where you recorded every state of the screen you'd ever seen and what action you should take. You know, if a laser's about to hit you right in a particular state of the screen, you should move left or right and get out of the way of it. And you could record all of those, right? Or could you? I naively, I don't know why I did this, it's a very silly thing to do, calculated it, or tried to put it into my calculator. It doesn't work right. If you think about it, this is 84 by 84 pixels, this screen. If you want to store all the possible states, that's 2 to the power 84 by 84, and that's a very big number. So you need something that can generalize, doesn't have to store them all, but can know that it's seen a screen that's similar to something it's seen in the past, knowing what action it needs to take. And that's what the big box in the middle is. We're software engineers, right? We like using things as black boxes. So the convolutional neural net is the trick that you need so you don't need to memorize every possible state of the game. What you do is you feed it a bunch of screen frames, and for each screen frame, it tells you whether you should move left, right, fire, or do nothing. It doesn't say just give you one output. It actually assigns a value to each one of these things. It says if you move left, the maximum value, the value of doing this is a certain number, and that'll be more than doing nothing if a laser's about to hit you. So you know that you basically take the maximum and do that action. And the neural net doesn't store every screen frame, it generalizes. When you get a particular screen frame, it looks and goes, I've seen something similar to this in the past, and when I saw this in the past, I did this action. And that's how it outputs those values. But we like understanding how things work, right? So this is my Dr. Crump version from secondary school. He was my chemistry teacher in year 7. And he always used to say, Dan, I'm going to explain things to you in a really simple way, because you might not understand if I did it the complex way. And a year later, he'd come back and tell me the way I explained it was completely wrong. It was inaccurate. I'm going to tell you how it really works now. And I'm going to do something similar with an explanation of a neural net. So, or convolutional neural net. Convolutional neural nets have, CNNs, have filters, which are these windows here, this yellow one, this orange one, and they slide, in effect, across the image, looking for particular things. So these windows, filters, slide across, and this yellow one may be looking for aliens, and it outputs a 1 if there's an alien there, or 0 if there isn't, naively speaking. And we've got another one that's like looking for the laser, another one that might be looking for the player, the shield, and the output of all of these together give you the current state of the game. And then you can make that association with what you should do. I think a key thing of saying with the filters as well is they don't know up front what they're looking for. They figure that out. But what does a CNN actually look like? I've been to a lot of deep learning talks, and I got this impression that it'd take a hell of a lot of code to create like a CNN, and then I was pleasantly surprised it's that many lines, you know, a handful. And that's it, that's what the CNN looks like. I always try and understand every code snippet in conferences. You don't need to, right? So here's our first input. This is input shape here is the size of our screen. And then we have a number of convolutional layers, these conv2ds. Well, just 2 in this case. And this 16 is our number of windows, our filters. And each filter is 8 by 8 pixels. You know, imagine detecting the aliens. In reality, what you get in CNNs is the first layer is detecting smaller things like edges of shapes, and like the lower layers are actually piecing those together and like detecting the full alien. And then finally, you're splitting out those outputs of left, right. So do nothing, fire, 4 in that particular case. Most of that. Then I highly recommend this book. So this book was written by the creative Keras. So the code snippet I just showed was in Keras, which is a framework that sits on top of TensorFlow. Everyone's heard of TensorFlow, right? For ML. And what this guy does really well is he explain stuff with code snippets without the maths. Each chapter starts explaining a different kind of neural net with a real use case, and then he runs through and solves it, and you can sort of follow along. And that'll help you really understand the CNN I've just shown. So here's the question. How does the CNN, convolutional neural net, figure out what actions are good and bad? It just plays, right? You just tell it to do random stuff initially. It's got this reward signal. It knows if it hits an alien, it's going to get some points in Space Invaders. But we've got to have some sort of strategy initially. So do random stuff and see how it works out for you. I know in the lead up to this talk, I'm sure I've put somewhere that there's not going to be any complex maps, and I'm really sorry. You're like, Dan, you just put some maps on. Just ignore this slide, right? If you look at this and you instantly go, what is this? Yeah, just like symbols, right? I'm going to do this in another way after this slide, but this is Q-learning. This is really important, so I wanted to put it up here so you could see it. And hopefully it ties back a little bit to what I've been talking about. It's always better when you've had a drink, but it's obviously 9:45 in the morning, so I'm not going to advocate that. So this is our table. Do you remember I said we could store all the states of the screen and what action you should take, how valuable it is to take an action? That's what this thing is here. You've got that table, the Q table. And initially, it's just all random. We don't know what's good to do or what isn't good to do. So lots of random stuff there. And we start doing random stuff, and every time we do something random, this may be a reward in the future, but let's just say now we fire a laser, we instantly get a reward for hitting, because we're ultimately going to hit one of the aliens on the screen. So we get a reward for that. We might get 5 points, might get 10 points. But the action of doing that actually puts us in another state. And from that state, there's a maximum score we can get. If we did the best thing possible from that point onwards, then we get the maximum possible score. So that's exactly what this horrible maths is saying. It's basically saying take the maximum action from the next state you arrive in, and then continue that strategy onwards. So working out how valuable the current state is a combination of these things, right? It's basically what you get now and what you could get in the future. And this might be like a stochastic, a random environment, so you have to just keep playing the game. You keep updating through this formula, and eventually you converge to the right answer. You'll know how valuable every state is and what action you should do in that state. And that's all this is doing, basically. Ignore the minus there. Basically, this is an update rule. You say, this is the random table of how valuable I think it is. I'll do something, and then I'm going to slightly move towards this, because my environment may be random. As I always do. Let's just do it a slightly different way. A simpler example, a more practical view of the world. So imagine you've got this world here, right? A robot starting down in the bottom right, and it needs to get to the gold. The robot can't see this world, right? All it can see is what's directly in front of it, the square that it's on. So it can't strategically plan where it should go and just take the best route. Also, part of the reason that Q-learning formula exists is because it accounts for sort of random stuff happening. You want to go left, but the wind blows you and you go off the grid square. But put that to the side for now. So we're going to start in the bottom right. I'm going to try and get to the gold. How do we work out how we should do that? Just imagine you might start anywhere in the environment, and we'll consider the square next to the gold. So we're up there. We want to sort of take as few steps as possible in this environment. We use energy taking steps. If we hit one of these bombs, let's say that's a real bad thing to happen, we'll lose 10 points. But if we get the gold, we get plus 10, we've won. So working out this square isn't too bad if we do it naively. If you go south, you're going to take a step, you're going to hit the bomb, you get minus 11. So it's a bad thing to go south. West, we take a step, we don't get anything right, that's minus 1, our rewards. But if we go right, we're on to a winner, right? We get plus 10 for getting the gold, but we took a step. So if we go east, we get that plus 9. That's our base case. If you've done like recursive programming, which I'm sure most people have, we bottom out here. Let's say we end when we get the gold. And as soon as you worked out that that's 9, right? You can work out everything else. You know that basically the best action here is to go right. But starting from this point, the maximum value you can get is 8, because -1, and the gold. So the maximum value of that state is 8. Similarly, you just follow it through, you basically lose in 1 every time. So, just working that through a little bit more. If you started there, it'd be really bad to go that way, because you're going to get -1, -10, -1, then +10. I think that's -2, my maths. Oh, I'll probably get it wrong, but who cares, right? See, -2 is less preferable than taking a step which puts you there. So going west is actually value 4 for you. Yeah, just ignore it. Don't worry about it too much. Doesn't matter. You know that the best action is to go, right, you don't want to hit bombs. Bombs are bad, so you're going to go west, north, east, and you're going to lose a point each time. And you just want to move towards where the maximum value is. So the agent, the robot, is in the bottom right initially. Doesn't really know where the gold is, so it's got to do this random stuff. But if we did random stuff all the time, it's not going to help us in the long run, because we're always going to stay in a particular part of the game space. So you've got to have a bit more of a better strategy for how you learn new things. Like if you start in the bottom right and you do random stuff, you might just end up staying in the bottom right of the screen forever, because randomly you just sort of end up back where you started. A bit like when I try and navigate a city. So you want a different type of strategy. As soon as you start learning what's good, you should start doing that. Like you've learned that going west is good. So most of the time I'm going to go west. But if you do that all the time, you're not doing any exploration. You might not figure out there's actually another bar of gold that's directly below you. So occasionally you should do something random. And if you combine these two things, taking the best action most of the time gets you further into the game and randomly helps you explore it a little bit and learn out new stuff, learn out there may be a better way of doing things. Oh, it's just a refresher, don't worry about it. But how does this fit into the neural network? So neural networks have training data, right? You have to feed it data, and you have to, if you're doing supervised learning, in this case we are, when you feed it input data, you have to give it some sort of value. You have to tell it what the correct answer is for that data. And this is how the deep learning stuff fits into the Q-learning formula. Our input into the neural network, ignore what the words are, don't worry about them too much. Our input is the screen frame, right? So you put the screen frame in, and we want the neural network to tell us how valuable each action is from that screen frame. Should we do left? Should we do right? How many points will I get in the long run if I take this movement to the left or right, or if I fire? And that Q-learning formula that I showed, it's just that part that goes in there, right? Basically, for this screen frame, that's how valuable a particular action is. So you remember earlier, I put screen frame in, it had a state getting spat out for left, right. That's a value, it's a reward and how much you're going to get from that point going forwards. So we train this thing, and then eventually we'll converge to the right answer. So I've been talking about single screen frames all along, which, again, I've been presenting a simple view of the world. This screen is dynamic. The aliens are going left to right. The lasers are either... there's an ambiguity there with lasers, right? The agent at the bottom can fire a laser that goes up to hit aliens, but also lasers come down. You've got to know which direction the thing's moving, which is quite a simple answer, really. So CNNs don't just have to operate on 2D data, they can operate on multi-dimensional data. So you just stack these screen frames on top of each other. If you look at the past few frames you've seen, you'll know if a laser's coming down and it's about to hit you versus if it's going away from you and about to hit an alien. And then you can make the appropriate decision. The exciting part, right? The exciting part, right? This is like playing Pong like a boss. It gets a bit tedious after you've watched it a while. I've seen this so many times now. You see, it realises it does no harm to do that erratic behaviour in the bottom right, as long as it goes up and hits the ball back at the right moment. And you see it gets into a bit of a cycle. It learns a strategy. This is a flaw with playing. Atari games are quite simple in a way, that the developers that coded them coded a strategy that's quite well, I think it is entirely deterministic. And it basically learns that if I fire the ball like this, it's always going to beat it. You'll see eventually, actually, it comes unstuck at one point and loses. And that's because my reinforcement learned trained agent on the right occasionally takes a random action, because what I learned was when I first trained it, it could get into the sequence where if my agent was completely deterministic, it could end up in a sequence where it just went back and forth the ball and it played on for days on end and never finished. They both just like had this standoff. So yeah, you know, pretty much beats it hands down, 21-3. It's not a bad start. When I first started looking at Atari games, one of the things you have to do in reinforcement learning is you have to decide what your reward function is. So I've been talking all along about the score in Space Invaders being the rewards, but it doesn't have to be. And how you choose your reward function in reinforcement learning can make your agent do really strange things. Because if it learns it's going to get like reward from doing something, it'll just keep doing that same thing, and it won't care about like the strategy of actually winning the game in the long run. When I first looked at Space Invaders, I thought, I'll be clever, right? I'll make this like really complex reward function where I'll match it up to the aliens, hit the mothership, I'll get loads of points. And if I get hit, then I'm going to really penalise the agent and say, if you get hit, that's a real bad thing. You should stop getting hit, right? And what I trained was something really conservative. It realised it should clear a column of aliens really quickly. But what it does is it learned to basically hide behind the shield. It goes, oh, if I come out, I might get hit, so I'm not going to come out very often. I'm going to hide behind there and just try and pick stuff off as it goes. Which, you know, it does all right. So I do have learning graphs for all of these. If anyone's interested after, I can show them. But this agent, basically, if you played lots and lots of games, the mean score was around like 500, 550. And that's the reason why it was so conservative that it never pursued to clean all the aliens from the screen. And if all the aliens get to the bottom, you lose. But it didn't care about it because it just thought, well, I'm going to lose lives, and losing lives cost me lots, right? And that really overweighed getting any of these rewards. So like round two, how does sort of changing the reward function affect playing Space Invaders? So you'll see it's a lot more aggressive than the previous player. It comes out from the shield and it actually goes after the aliens. That's because losing a life isn't so bad to it. It feels it can go out and start knocking these things off. Also, there's no waiting on the aliens, so it's not very discriminative about what it hits. It just goes out and says, I'm going to get the aliens, I don't care. And you see it does way better. So mean score, taking random actions in Space Invaders, about 200. Human players score about 600, I think, from like DeepMind. I don't know if DeepMind just got their entire team to sit and play Space Invaders for days and see how well they did. But they say human player gets about 1,600 on average. With the code I used, you should get up to a mean score of about 2,000 if you left it training for about 8 days. I blew up my charger for my MacBook. Don't do deep learning on them. I shouldn't say that. Yeah, it just went pop. And then I thought I'd pay for some like cloud resource to do this. And I actually use a CPU-based cloud resource because I'm tight. So this is a result after about 4 days of training, running solid, learning how to play Space Invaders. And the mean score it got was, it was about 1,200, but it was still going up, it was still learning more, and the DeepMind guys, they topped out at, I don't know if they topped out or they just stopped training at 2,000 points. It'd be interesting if you had the will and the money to pay to see how far you could get. But you see, it does quite well. But also, it generalizes quite well, because the next part of as soon as you clear the aliens once, right, the next part of the game is the same again. They just move a little bit faster. So as soon as you get past one game, you're good to go on the next. You'll get quite far. So the bits that I didn't talk about. Feel free to completely switch off, right? If you'd like, just listen to me and thought, I don't know what he's on about. Yeah. Don't worry about what comes next. So neural nets are normally trained, reinforcement learning is like a new thing. Those papers in 2013, it was like new to get neural nets properly working with reinforcement learning. And they don't expect training examples to be correlated. If you think about like a spam classifier, you feed it a bunch of emails, you say each email is spam, not spam. But each email is generally independent. Like someone emailing your inbox, the next person that emails isn't, they're not related in any way. Those messages aren't necessarily related in any way. It doesn't quite hold up, I know, but almost independent. Whereas playing a game, right, it's sequential. You take an action, you see a new screen frame. You take another action, you see a new screen frame. There's a linear dependence on these things. And it turns out that neural nets really don't like that. They get very upset. So what you have to do is maintain this idea of a replay buffer. You basically store all the screen frames you've seen in the past, what action you took, how valuable they were. And when you train your neural net, you randomly sample this, and it removes that sort of correlation and helps the neural net learn new things. And if you don't do that, you get a significantly lower score. It's that formula again, right? It doesn't go away. Same one, though. Best actor in the world, right? Ethan Hawke. So no one agrees. But he's one of those beautiful actors, right? He does every genre, like romance, Before Sunrise, Before Sunset, classic, but horror, Purge. But sci-fi Ethan Hawke is the best, right? He's awesome. I've asked like 2 rooms of people if they've seen Predestination, and no one said yes. So I'm not going to spoil it, because you all should go away and watch Predestination, because it's an awesome film. But the reason there's a problem with this is because of Ethan Hawke. That's one of the problems you encounter when you try and train a neural net. The snake that eats its own tail is the best description I probably can give. So you're training this thing. The neural net is effectively learning, approximating what this Q table should be, all the states in the world and what action you should take and how valuable they are. But the way you're training it is through this formula, right? You take an action, you get a reward, and then you've got to figure out the state it puts you in, how valuable that is, how well you're going to do in the game from that point onwards. But if you're just starting out and you've not played loads of random actions and you've never experienced the game, how do you know how valuable your next state is, right? You may have never even played on from that point. You don't know what score you could get from that point. So you have to cheat a little bit. And what you do is you use the thing you're training to make the prediction of how valuable that state is. That's nonsense, right? It's like this Terminator loop where you go back to save Sarah Connor, and then there's another film in the franchise, and it gets even more convoluted. And before you know it, the whole premise just falls apart. So you have to decouple these things in a way, and it's a bit of a cheat, really. What you do is you periodically take a copy of the neural network that you're training, and then you use that. You use the Q table that you had at a period in time, and you basically use that to make predictions. And when it starts getting horribly out of date, you copy it again. So you've effectively got a stale copy of the thing you're training to make the predictions. And it's like trying to remove a correlation. And if you really, if you see this talk and it inspires you to go away and, actually code this stuff yourself and have a go, and, there's lots of Atari games you can try, pick any above that line. The racing one's particularly good, and the Lunar Lander, that's a good game to have a go with. You can even probably try my code on it. It should just work if you want to pay for some, cloud credits to actually train it for a few days. So that thing got me horribly. So neural nets learn through gradient descent. I suppose skiing is again, a real simple view of the world. Imagine this is your error curve. Like, your neural net is trying to make a prediction of how valuable a state is. But then there's, like, how valuable the state really is, right? And it's the difference between the two, right? So you take an action, you know what rewards you got. How does it compare to what you thought you'd get for taking that action? And then you look at the error, right? And the neural net over time is trying to minimize that error. So basically, you want to slide down this curve to get to the bottom and have the lowest error possible on your predictions. They need to be as close to reality. So you do gradient descent. Basically, you look at where you are now, where you should be, and then you want to jump a little bit towards where you should be. If you jump too far, you may completely miss where you're going. If you jump a little bit, it'll take you ages to get down here. You want to sort of get down here nice and quick. And the learning rate is one of those things that helps you get down there. The problem is if you set it too big, you can end up bouncing around here. Worst case, you can even just blow up and never learn anything and completely just carry on playing Space Invaders like a completely random agent. And reinforcement learning takes a long time. You need to run it for a few hours to really get a feel for if it's working or not. So I spent hours trying to debug. I thought I had my code wrong. And it turns out, like, the defaults that ship with the learning rates for most gradient descent optimizers, they weren't appropriate for my problem. But that, again, a simple view of the world. It's a number that you tune. All of my material. So I'm happy to take some questions.
So we need to ask the questions on the mic, so we just...
I just had a couple of questions. When you're training your model against the Atari games, do you get to play them in real time or double speed, quadruple speed?
So there's multiple, in terms of sort of seeing how it's progressing, or actually how it's being trained. So there's different elements to this. So in terms of the training, one of the things, the replay buffer of remembering like a whole bunch of stuff you've seen in the past and what action you took and how valuable that was, because you typically buffer up a lot. So I was buffering up about 800,000 states. And then you can basically train your neural net faster than you're playing the game because you've got this whole wealth of experience of how you played in the past. So in reality, you take one new step, that goes into the buffer, but then you train from lots of steps you've seen before, sampled randomly. So you're sort of learning at a rate faster than real time. In terms of playing these things, it's as fast as you can like drive the API. So you're calling out to OpenAI Gym to basically say, take an action, it gives you a frame back. So, it's quicker than if you sort of sat and watched it. It's sort of that action, get a response straight away, and as fast as that happens, you can keep going and play the game. In terms of sort of monitoring when you're training, I think it's probably worth talking about. So when you're doing reinforcement learning, to see how well you're doing, you normally monitor what the reward is for how you're going currently. So you're basically training by playing lots of games, right? So each game you sort of record what score you got in that game, and you can keep tabs on, like, I've done another game in training, I got this score, I've done another game in training, I got this score, and you can basically plot a curve of how that score's going, so it gives you a good indication of if you're learning something and you're getting better at the game. Is that okay?
Just a quick one. Just when you're looking at the screen buffers and say Space Invaders sort of detecting when you have hit an alien, is that something you had to do, or was?
Yeah. So the question there about detecting when you've hit an alien. So that the score is you get as well as the screen frames coming back from the game, you get the current score. You also get the number of lives you've got. So that's how you can make decisions about what your rewards should be. I think the thing that I sort of said briefly in there is this all holds for like future rewards the sort of formula plays out that it's fine that if you fire a laser, it will correlate that will eventually hit an alien, and it sort of propagates back through the formula. So you know that firing a laser now is going to give you some sort of reward in the future. It's got that temporal thing in there.
Anyone else?
Hi. How do you interface it to the game? For example, how do you know that a Space Invader's been hit?
Okay, so in terms of how you know a Space Invader's been hit, in terms of what the agent actually knows in terms of learning, it's not really aware that it's hit an alien. It only knows that it got a reward, and that's whatever you code it to be. So in the sort of the simpler example I showed, where you just got like +1 point for hitting an alien, you know, that's its naive way of knowing that it hit an alien. It got a point at some point. It got a point for doing something good. It doesn't necessarily care that it hit an alien. It just knows it got a point, and whatever it did to do that, it should do again.
What I really meant was, I mean, you don't have a camera looking down at the screen, seeing that an invader's been hit. How does your AI know that it's been hit?
So there's
How
two.
do you interface it to it?
Yeah, so it's basically I suppose it's a camera indirectly, right? Because you know what the pixels are on the screen. So you get that 3D array of RGB for what the screen looks like. So it's almost like you are looking at the screen, you know, and that's what input goes into the neural net. So yeah, it is almost like you've got some sort of vision aspect that's looking. So that's how it knows what's on the screen currently, and then obviously the reward is what it's matching it up to at the other end.
So you translate the game score into the rewards?
Yes, so you could naively just take the game score and just use it as rewards with a bit of fudging, but you can do like some munging on it to change it to be like whatever. Like all of the games a lot of them don't punish you for losing a life, and you can manually, as I did, encode that in to say, well, you get -1 if you lose a life. But it'll know because of that 2D buffer that what the screen looked like just before it lost a life.
I was wondering if you tried using the vertical position of the aliens as some kind of, you know, extra reward for hitting aliens that are lower down the screen.
So I think that touches on like completely going slightly off topic, but it touches on a really interesting point of why deep learning. So the way people have tried to do this in the past is you can do feature engineering, right? You could basically write your own algorithm to look at the screen frame and encode the XY position of all the aliens and where the laser is, and actually use that as your feature array. And then you could use your own shallow ML classifier to make a prediction about what you should do. And similarly, you could augment additional stuff into those features. The joy of the deep learning stuff, and probably why it's such a breakthrough, is, and why everyone's sort of mad for deep learning at the moment, is you don't have to necessarily do that feature engineering. In this case, you're not doing any feature engineering. You're giving it a 2D view of what the screen looks like, and you're saying to it, you figure out that you should go looking for aliens. I'm not going to even tell you there's aliens on the screen. And that's sort of naively what the filters are doing in the CNN. They're really figuring out what coordinates the aliens are at and where the laser is and where the shield is, and then using that to make a determination of the action you should take. But I know one of my colleagues did like Pong just with feature engineering. It is doable. You can do these things. You can develop a strategy. If you know where the paddles are and the ball is, you can make those decisions.
Quick question.
Hi, thanks for the really interesting talk. I was wondering, has there been much success in doing transfer learning between different games, maybe quite different games or maybe very similar games?
Yeah, so I'm gonna defer that question onto the reinforcement learning experts. I did most of this as part of my degree for the fun of it, and my sort of ML background is mostly NLP, and obscure indoor positioning. But it's an interesting topic because I've chatted to people after giving this talk, and they're looking at using Unity to train agents like autonomous cars and stuff. But then is that really going to transfer in the real world? I suppose my really naive, naughty observation of this is the Atari games are deterministic, and basically they will not cope very well at all if you then put a human player in the mix, because a human player will instantly do something that it's never seen before and not cope with that. But yeah, interesting on the transferable aspect. I'm sure there's probably 2 Atari games you could get that are quite similar, and then give it a go and see if you could take the weights you've got and have a go and see if it bootstraps it to start.
Awesome. Okay, we just have one more question and then we'll finish.
Yeah, thanks for a great talk. There's been a lot in the press about the game of Go and AlphaGo and DeepMind. I mean, is there potential for kind of transferring this to games or scenarios where there's a great deal more complexity and the level of decision making or creativity or intelligence is kind of more challenging than an Atari game?
So what I'm going to do is plug our chair for the day, Rich, who's doing some of this really interesting stuff. So if you go up to him, he'll maybe give you a description of your particular use case.